welcome to another podcast. We're going to be talking about calculating the pH of acids and bases today and looking at strong versus weak. So I hope you enjoy this one. I enjoy doing them for you. Alrighty, so let's start with what a strong acid or a strong base happens to be. Strong acids and bases are classified as such because they will completely dissociate in water. A lot of folks think that it has to do with their pH, and really pH is not the determinant in whether an acid or base is strong. You can have a strong acid that doesn't have an exceedingly low pH. You can have a strong base that doesn't have an exceedingly high pH. The strong acids and bases are also known as strong electrolytes because they do completely dissociate in water. And when they completely dissociate in water, that means that they exist as their ions. So since you have free-floating ions floating around in the water, you can conduct electricity. The understood strong acid list is hydrochloric, nitric, perchloric, and sulfuric. And the understood strong bases list includes the alkali metal hydroxides. If you recall, the alkali metals are the group 1 metals, starting with lithium going down to francium. So for example, if you have lithium hydroxide, it's classified as a strong base. Every other acid and base that you encounter will be classified as a weak acid or base. They are considered weak because they do not completely dissociate in water. And they have varying levels of dissociation, unlike strong acids and bases. Strong acids and bases completely dissociate in water, period. Weak acids and bases can dissociate a lot, a little, whatever the particular acid and base we're talking about wishes to do. The less dissociated they are, the weaker they are, and that means the weaker electrical conductivity they will have. Obviously, the converse is true. The more dissociated they are, the stronger they are. And you recognize acids typically because they have a hydrogen ion at the beginning of the formula. Weak bases are a little more difficult to recognize, so I want you to look for the presence of an amine group, which is a nitrogen with a couple of hydrogens bonded to it. We'll kind of use that as a good reference. Alrighty, we're going to start with calculating the pH of strong acids. So the first thing I want you to do is write the dissociation of hydrochloric acid, HCl. Again, recognize that it is a strong acid. It will completely dissociate, so it doesn't really exist as HCl. It exists as just its ions. Once you get that dissociation written, I want you to recognize that it should have a one-way arrow in it. Because it has the one-way arrow, it tells us it goes to completion, that it completely dissociates. So you should have HCl aqueous yields hydrogen ion that is aqueous and chloride ion that is aqueous. And what we're going to do is figure out the pH of a 12 molar solution of concentrated HCl. That's the largest concentration that HCl can have. Different acids have different maximum concentrations, and HCl's happens to be 12 molar. So what we're going to start out doing is drawing a chart to indicate the progression of the dissociation. When we do so, the HCl initially starts out with 12 molar. The hydrogen ion and chloride ion are both 0 initially. Because it goes to completion, the change in concentration will reflect the mole-to-mole ratio as always, but we need to recognize that the HCl is our limiting reagent, which means it will be completely used. So the change in concentration for the HCl is that it decreases by 12 molar. Well, reflecting the mole to mole ratio of 1 to 1 to 1, that means that the hydrogen and chloride ions change in concentration will be plus 12 molar and plus 12 molar respectively. Your final concentration, notice it doesn't reach equilibrium. This is not an equilibrium chart. This is actually a stoichiometry chart, if you will. You will not follow it with an equilibrium chart because this particular dissociation does not reach equilibrium. So our final line for the HCl will read 0, for the hydrogen ion, 12, and for the chloride ion, 12. What you should be able to recognize at this point is that the hydrogen ion is 12 molar. which means you can determine the pH of the solution, as you've already learned how to determine pH. You recall that you determine pH by taking the negative log of the hydrogen ion concentration, and since we plug in 12 molars as our hydrogen ion concentration, the opposite log of 12 happens to be a negative value. This can be a little disconcerting to a lot of folks who believe that the pH scale ranges from 1 to 14, some folks have been told, or 0 to 14. Well, unfortunately, that's not quite true. So the pH of 12 molar hydrochloric acid is actually negative 1.08. Again, that very low pH does not necessarily tell us this is a strong acid. It tells us that the hydrogen ion concentration is large. That is all that pH tells us. Remember, it's the power of hydrogen ion. Since it dissociated completely and the equilibrium was never reached, you really didn't need to make a chart. Because if you realize that HCl dissociates completely and that you really don't have any HCl, you really just have hydrogen ion and chloride ion, if you know it's 12 molar HCl to begin with, then you know it's going to end up being 12 molar hydrogen ion. So all you have to recognize is that you have 12 molar hydrogen ion and go to town with that one and get yourself the pH. Alrighty, let's look at determining the pH of concentrated sulfuric acid that is 18 molar. I'm going to introduce a concept to you here that I'll come back to later on in this particular podcast, but I do want to introduce it now to show you that the one strong acid that has two hydrogen ions is known as a diprotic acid. Diprotic means two protons, the protons of course referring to the hydrogen ions. That means that there are two hydrogen ions that are able to dissociate in sulfuric acid. However, only one hydrogen ion dissociates at a time. So the first dissociation takes H2SO4 and it completely dissociates into hydrogen ion and hydrogen sulfate ion. That means it gets a one-way arrow. The second dissociation starts with hydrogen sulfate ion and further dissociates, but you'll notice hydrogen sulfate ion, HSO4 negative, is not on your list of strong acids. So we classify that one as a weak acid, which means it gets a reversible arrow. And when it dissociates, it gives us more hydrogen ion and sulfate ion. So we get hydrogen ion from both dissociations, but I do want you to understand that when you have what's called a multiprotic acid, the primary giver of hydrogen ion is the first dissociation. The second dissociation in this particular case doesn't generate as much hydrogen ion, so it's really the first dissociation that determines pH. We'll work some more in-depth problems a little bit later on multiprotic acids, but for right now, let's just assume that we know the hydrogen ion concentration to be 18 molar because this was 18 molar sulfuric acid. We know it will dissociate to give us hydrogen ion and hydrogen sulfate at the same concentrations due to the 1:1:1 ratio, which is always going to be the ratio in the dissociation of acids and bases, by the way. So you take the opposite log of 18 and you get the pH of 18 molar sulfuric acid to be negative 1.255. Alrighty, let's do the same thing but with a strong base. I want you to write the dissociation of sodium hydroxide. We know it's a strong base because it's sodium, which is an alkali metal, with the hydroxide ion. So we don't ever really have a solution of sodium hydroxide. We have a solution of sodium ions and hydroxide ions floating around in water. When you write its dissociation, it should have a one-way arrow indicating the complete dissociation. You should have aqueous sodium ion and aqueous hydroxide ion as your products. Let's determine the pH of a 6 molar solution of sodium hydroxide. Again, you don't need to make a chart. If you wish to, you can, and if you were to make a chart, you would have an initial change in final line. Again, it doesn't reach equilibrium. And you would understand that your initial concentration of NaOH is 6 molar before anything dissociates, and your sodium and hydroxide ion concentrations are 0 molar. Your final concentrations respectively would read 0, 6, and 6. So again, you don't have to do a chart when you're working with strong acids or strong bases, and I'm just going over it with you just for reaffirmation of your knowledge. So if you know that you have 6 molar hydroxide ion concentration, then you're able to determine the pH in a little more detailed process than you did with strong acids. So the first thing I suggest you do is take the opposite log of the hydroxide ion concentration to find the pOH. Once you find the pOH, which is negative 0.778, then realize that pH plus pOH always equals 14. Be very careful with your signs here, which means we can take 14, subtract negative 0.778 to get the pH, and we therefore find the pH to be 14.778 or 14.823 significant figures. Again, you see that the pH scale does not stop at 14. It can be above 14 just as it can be below 0. Alrighty, so I think you've mastered strong acids and strong bases. Pat yourself on the back, give yourself a round of applause, whatever it is you feel like you need to do, because we're about to jump into weak acids and weak bases, which get a little more complex, but they're not too bad, especially since you've already worked equilibrium stuff, is my hope. Alrighty, I want you to first write the dissociation of the weak acid acetic acid, which is HC2H3O2. Now, I know it's weak because it is not on the list of strong acids. So remember, any acid that is not on the list of strong acids, that list included hydrochloric, nitric, perchloric, and sulfuric, then it's considered to be weak, which means it will reach equilibrium. In turn, that means you will have a reversible arrow in the dissociation. So when you write your dissociation of HC2H3O2, I want you to recognize that it is the first H that dissociates. This is not a quadra or tetrapodic acid because it has 4 hydrogen ions in it. It does indeed have 4 hydrogens in it. However, the only dissociable hydrogen is that first one. The other 3 hydrogens are embedded in the acetate ion, and they will not dissociate in water. So your dissociation will generate 1 hydrogen ion and 1 acetate ion. The two-way arrow again indicates to us that it reaches equilibrium. We're going to work on calculating the pH of the maximum concentration of acetic acid. It's called glacial acetic acid, by the way. It's found in the stop bath that's used in developing photographs, if any of you are familiar with that. And the maximum concentration of acetic acid is 17.4 molar. It smells like a really, really stout vinegar solution because it's all it is. Okay, I want you to realize that it's weak, it reaches equilibrium. Since it reaches equilibrium, it will have an equilibrium constant. The equilibrium constant of a weak acid is guaranteed to be a small k value, which means that the reaction prefers to make reactants. It doesn't like to go very far to the right, is what that means. Well, since it has an equilibrium constant, we're going to make it a little more specified, and we're going to call that constant a Ka. The A standing for acid, of course. No tricks there. Alrighty, next thing we need to do is write a Ka expression for the dissociation of the acetic acid. If you recall, you put products concentrations raised to the power of their coefficients over reactants concentrations raised to the power of their coefficients, and you include aqueous and gaseous substances, you exclude liquids and solids. So when you write your Ka expression, it should read Ka equals the concentration of hydrogen ion raised to the first power times the concentration of acetate ion raised to the first power divided by the concentration of acetic acid raised to the first power. Again, that mole to mole to mole ratio for any acid or base dissociation will be 1 to 1 to 1. Tends to make your life a little easier. The Ka value for acetic acid is 1.76 times 10 to the negative fifth molar. I'm not going to be a stickler on the units when we work out problems of weak acids and weak bases. They're all going to have the same units. Alrighty, next step is to make a chart for the dissociation. You should recognize that we're making an equilibrium chart. We are making an equilibrium chart because this reaction will reach equilibrium and because this is a small K value. That K value being less than 0 indicates to us again that it likes to make reactant more than it likes to make product. So in your equilibrium chart, you have an initial line that reads 17.4 molar for the acetic acid, 0 and 0 for the hydrogen ion and the acetate ion. It's 0 and 0 for the ions because no dissociation has taken place yet. The change line of an equilibrium chart, remember, always reflects the mole to mole to mole ratio. And since it's an equilibrium chart, we use variables because we don't know how much will dissociate from the acetic acid. Because it's a 1 to 1 to 1 ratio, we're going to understand that the mole to mole to mole ratio in terms of x will be 1 to 1 to 1 as well. So your change line is going to read minus x, and plus x. At equilibrium then, you're going to have 17.4 minus x, and x respectively. Your next step is to plug into your Ka expression. Pardon me. And in doing so, you're going to plug in 1.76 times 10 to the negative fifth as your Ka value, equals x as your hydrogen ion concentration at equilibrium, times x as your acetate ion concentration at equilibrium, divided by 17.4 minus x. Now, if you recall, we can pull out the minus x, making an assumption that that amount of x we subtract from 17.4 is so small that it doesn't make a difference. We do that, but then we must test the 5% rule. So as you pull out the minus x, it makes your math much easier. And when you then solve for x by multiplying 17.4 by 1.76 times 10 to the negative fifth, and then taking the square root of both sides, you will get x to be 0.0175. Well, to test your 5% rule, take 0.0175, divide by that from which you pulled it, and multiply by 100, and you'll get your percentage. I get that percentage to be 0.1%. That's indeed less than 5%, which means that my assumption that x was small enough that it didn't make much of a difference was a good assumption. In other words, if I were to have left the minus x in and used the quadratic formula to solve for x, I would have gotten essentially the same value of x, and it would be a lot more work to solve for x using the quadratic than it was in the manner in which we solved it. So, now think about what x represents. It is, from your equilibrium chart, representative of the hydrogen ion concentration. Well, once you know something's hydrogen ion concentration, you know that you can find the pH, and that was what you were asked to find. So you take the opposite log of this value of x, 0.0175, and you get the pH of 17.4 molar acetic acid to be 1.76. Again, it's a weak acid, but I don't want you to think that because it's a weak acid, it needs to have a pH closer to 7. Weak acids can have low pHs, just as strong acids could have higher pHs. Again, pH is the power of hydrogen ion. It's all dependent upon the concentration of hydrogen ion. Okay, you just worked a weak acid problem. Give yourself a round of applause again. Ought to get pretty noisy around there, huh? Okay, now you're going to solve for the pH of a weak base. And I want you to write the dissociation of the weak base ammonia. Notice it is not ammonium, ammonia, which has a formula NH3. Now I'm going to give you a handy little tip that you need to definitely pay attention to. Every time you write the dissociation of a weak base, make sure that you write that that weak base reacts with water. That is going to be your justification for producing a hydroxide ion. Alrighty, so you need to write that ammonia reacts with water. The ammonia, not that I expect you to know this, is a gas. So when we make a solution of ammonia in water, we are pumping the gas ammonia into water. It's a weak base, so it will start to dissociate but will not go to completion. It prefers to keep its reactants, but it will indeed make some products. Now remember, a base, according to Bronsted-Lowry, which is our most prominent method of classifying acids and bases, according to Bronsted-Lowry, will accept a proton. The reason I asked you to write that the ammonia reacts with water is so that you have justification for where it got a proton. It steals a hydrogen ion from water. In doing so, it makes ammonium ion, NH4 positive, and it leaves behind hydroxide ion, OH1 negative. Both of those ions are aqueous. Now notice that you have liquid H2O as a reactant. Remember that when we write K expressions, we only include gaseous and aqueous phases, which obviously tells us we're going to exclude the water. We are going to calculate the pH of an ammonia solution that is 15.3 molar. Again, we will have a Kb value because this is going to be a base dissociation. It will reach equilibrium. Anything that reaches equilibrium has a K value, and the Kb value for this particular base is 1.75 times 10 to the negative fifth molar. Yes, it's a very similar K value to that of acetic acid, but I promise you not all Ka and Kb values hover around those numbers. So I would like for you to write your Kb expression. Again, products raised to the power of their coefficients divided by reactants raised to the power of their coefficients, only including gaseous and aqueous phases. You will have Kb equals ammonium ion concentration raised to the first times hydroxide ion concentration raised to the first divided by ammonia concentration raised to the first. Notice water is not present because it is a liquid. The next thing you want to do is make a chart for the dissociation of water and indicate that it will reach equilibrium. Again, our initial concentration is 15.3 molars, the maximum concentration that I can have of ammonia in water. So my initial line will read 15.3, 0, and 0. It's going to reach equilibrium, which means on my change line I'm going to have variables, and I'm going to reflect the mole to mole to mole ratio, which again is 1 to 1 to 1. So the ammonium 15.3 initial concentration will go down by X. The ammonium ion initial concentration will go up by X, and the hydroxide ion concentration initially at 0 will go up by X. At equilibrium, then, we're going to have respectively 15.3 minus X, X, and X. You plug into your Kb expression. 1.75 times 10 to the negative fifth equals X times X divided by 15.3 minus X. Solve for X by pulling out the minus X and testing the 5% rule. It's always quicker to do that than it is to set up the quadratic. If it obeys the 5% rule, that's great, and you can go on your way. If it doesn't, you simply have to go back and use the quadratic. So in this particular case, when I take 15.3 and multiply it by 1.75 times 10 to the negative fifth, take the square root of both sides, I find that X is 0.0164. When I divide that value of X by 15.3 from which I pulled it and multiply by 100, I get it to be 0.107%. Indeed, less than 5%, so I accept that value of X as being an accurate value of X. Now go back to your chart. Notice that X was representative of both the ammonium ion and the hydroxide ion. We can find pH, but remember, we are dealing with the hydroxide ion's concentration right now. So the first thing I suggest you do is find the pOH. Take the opposite log of the hydroxide ion concentration, which is 0.0164. You should find pOH to be 1.79. Subtract the pOH from 14 to get the pH. So 14 minus 1.79 ends up being 12.2 to 3 significant figures. You verify it's a logical pH because it is a basic pH. Again, we're dealing with 25 degrees Celsius. I'm not changing that on you. So we know neutral is 7 and anything above 7 should be basic. So indeed, we do have a basic pH. And don't be alarmed that it's pretty close to 14, even though it's weak. Remember, pH is simply dependent upon the concentration of hydrogen ion. Okay, you are almost finished. The last thing we're going to do is look at determining the pH of a multiprotic weak acid. So I want you to write the dissociations, notice plural, of tartaric acid. Tartaric acid's formula is H2C4H4O6. Little cocktail info, we find tartaric acid in cream of tartar, the stuff that you use to make tartar sauce. It has 2 dissociations because it is a diprotic acid. I know it is diprotic because it has 2 hydrogens sitting on its forward end. The 4 hydrogens embedded in the tartrate ion are not dissociable. So it has 2 dissociable hydrogens, therefore it is diprotic. I know that it's a weak acid because it's not among my list of strong acids. So the first dissociation is going to take H2C4H4O6 and dissociate it into one hydrogen ion and HC4H4O6 1 negative. Now remember, it can only dissociate one hydrogen ion at a time. The second dissociation takes that which is produced that can still dissociate a hydrogen, in this case it's called the hydrogen tartrate ion, and dissociates it further. So the second dissociation starts with hydrogen ion concentration and hydrogen tartrate. The hydrogen ion concentration can't dissociate any further, but the hydrogen tartrate can. So I dissociate it into further hydrogen ion and tartrate ion, which is C4H4O6 2 negative. Notice its charge became 2 negative when I pulled another hydrogen off of it. So I want you to notice both reactions produce hydrogen ion. As I told you earlier, the first dissociation is the dominant supplier of hydrogen ion, but in the case of a weak acid, we cannot assume that all of the hydrogen ion that determines pH is produced in that first dissociation. We do have to look at both of them. Because there are two dissociations, it means there are two equilibrium constant values. They are reported as Ka1 to indicate the first dissociation's constant and Ka2 to indicate the second dissociation's constant. So we're going to make this problem a little more complex, and we're going to figure out the pH of a 100 milliliter solution that contains 5 grams of tartaric acid. Ka1's value is 9.2 times 10 to the negative fourth. It does have the unit of molarity, but again, I'm not stressing that unit. And Ka2's value is 4.31 times 10 to the negative fifth. And again, it does have the value, the unit of molarity, but I'm not stressing it. All right, well, notice in this one that I've told you we have a 100 milliliter solution that contains 5 grams of tartaric acid. Heretofore, I've given you molarities, and I've not made you do that much work. Well, you know that I'm going to make you do some work, so anytime you're given the mass of a substance, chances are very good that you need to find the molar mass of that substance so that you convert the grams into moles. So your first step is to determine the initial molarity of that tartaric acid. In doing so, you calculate the molar mass of H2C4H4O6, and you should find it to be 150.1 grams per mole. Well, that means you're now going to set it up so that you have 5 grams times 1 mole over 150.1 grams. Your grams will divide out. It'll leave you with moles. I can then find the molarity by dividing those moles by my volume in liters. So you need to convert 100 milliliters to liters, and 100 milliliters is 0.1 of a liter. So I take my moles and divide by 0.1 of a liter to get an initial molarity of 0.333 molar. That is of my tartaric acid. So I'm ready to go now and make my first chart. Yes, you're going to have 2 charts because you have 2 dissociations. So the chart for the first dissociation looks at the fact that we have tartaric acid becoming hydrogen ion and hydrogen tartrate ion. Your initial line will read 0.333, 0, and 0. This ought to become old hat by now. Your change line reflects your mole to mole to mole ratio and should read minus x plus x plus x. And at equilibrium, you're going to have 0.333 minus x, and x. Your next step is to plug into your first dissociation expression, your Ka1 expression. So if you write your Ka1 expression, put the products of the first dissociation in the numerator raised to the power of their coefficients divided by the reactant raised to the power of its coefficient. Then you're going to plug in your Ka1 value, plug in your equilibrium concentrations in terms of x, and solve for x. You may certainly remove the minus x and solve for x, test the 5% rule, and see if it works. If it doesn't work, then that means that you need to conduct the quadratic. Well, I'll give you a moment to do that, and I'm warning you that you're going to have to use the quadratic to solve for x. Sorry about that, but it happens from time to time. So since we have to use a quadratic formula to solve for x, we need to recognize that we're going to have 0.333 minus x multiplied by 9.2 times 10 to the negative fourth. That will equal x squared. Remember to get everything on one side so that it is equal to 0, and you have it in the format of ax squared plus bx plus c equals 0. Now what you might do is stop the podcast at this point and work through to find the value of x using the quadratic, because I'm not going to sit here and wait for you to do so. So once you do use the quadratic to solve for x, you get x to be 0.0170. That is an accurate value for x. Now remember the x represented from our first dissociation's equilibrium chart the concentration of hydrogen ion. It also represented the concentration of hydrogen tartrate, and that is a very important point. I'm not going to stop at this point and find pH, because I need to recognize that more hydrogen ion is dissociated in the second reaction, and I need to determine whether that additional amount of hydrogen ion is enough to change the pH. So I'm going to make my second equilibrium chart for the second dissociation. Notice that you have hydrogen tartrate, HC4H4061 negative, becoming hydrogen ion, and tartrate ion, C4H4062 negative. My initial line, you need to be very careful with this, is dependent upon what I got at the end of my first dissociation. So it's critical that you do that first dissociation properly, otherwise you're guaranteed to mess this part up. Now realize that we solved for x in the first dissociation, and x represented both the concentration of hydrogen tartrate and the concentration of hydrogen ion. So what that means is my initial concentration of hydrogen tartrate is 0.017. My initial concentration of hydrogen ion is also 0.017, because I have those two ions present initially from the first dissociation. My initial concentration of tartrate ion is indeed 0 because I've not yet seen it. My change line is still going to reflect mole-to-mole-to-mole ratio and still going to use variables. So my change line is still going to read minus x, and plus x. Now it is plus x for the tartrate ion, obviously because it started out at 0. It is plus x for the hydrogen ion because it happens to be a product along with tartrate ion. And if one product's concentration goes up, so does any other product's concentration. If those two went up, then it is only logical that the reactant's concentration had to go down. That means at equilibrium, I'm going to have 0.017 minus x, 0.017 plus x, and x. I then plug into my Ka2 expression. Be careful, make sure that you choose the proper Ka2 value. And in your expression, you should have Ka2 equals concentration of hydrogen ion raised to the first times the concentration of tartrate ion raised to the first divided by the concentration of hydrogen tartrate ion raised to the first. When I plug in, I realize that I have 4.31 times 10 to the negative fifth equals 0.017 plus x times x divided by 0.017 minus x. Now in testing the 5% rule, remember I can remove any amount of x that has been added to or subtracted from an initial quantity that was not 0. That means you can draw a circle around the plus x and around the minus x and kick them out and behold the beauty of what you have remaining. Do you notice you can divide 0.017, x by 0.017, and lo and behold, x equals 4.31 times 10 to the negative fifth. Aren't you excited? You still have to test the 5% rule, which means take that value of x, 4.31 times 10 to the negative fifth, and divide it by 0.017. And indeed, it obeys the 5% rule, and you can accept that value of x. Now realize that value of x represented the tartrate ion concentration at equilibrium. But it was also the amount of hydrogen ion that dissociated from the second dissociation, which means as I look at my equilibrium chart, I see that the concentration of hydrogen ion at equilibrium after the second dissociation read 0.017 plus x. Well, now that I know what that second value of x is, 4.31 times 10 to the negative fifth, and I add it to 0.017, I think we can all see that it doesn't really make that much of a difference in the hydrogen ion concentration. It becomes 0.0170431. Well, when I take the opposite log of that value versus the opposite log of 0.017 to three significant figures, I'll get the same pH. And when I take the opposite log of either 0.0170 or 0.0170431, for those of you who are so anal retentive, you will get a pH of 1.77. Okie dokie. Again, a round of applause because you just calculated the pH of a multiprotic acid. I'm going to go one step further and ask you to give me the equilibrium concentrations of all of the species. That means go back to each chart's equilibrium line and analyze it for what you said the equilibrium concentration would be. Well, in the first chart, you said that the tartaric acid's equilibrium concentration would be 0.333 minus x. And the value of x in that first dissociation was 0.017. So the tartaric acid's equilibrium concentration is 0.333 minus 0.017, which is 0.316 molar. The hydrogen tartrate ion concentration, you said in the second dissociation chart, remember we need to look at the last place we see it, would be 0.017 minus that second value of x. Well, that second value of x was 4.31 times 10 to the negative fifth. So 0.017 minus 4.31 times 10 to the negative fifth happens to be 0.01696 molar. Essentially to three significant figures, 0.0170. Didn't change it significantly. The tartrate ion concentration, we said at the end of the second dissociation, would be equal to x. Well, x in the second dissociation was again 4.31 times 10 to the negative fifth, and we understand that that is the unit of molarity. You already know the concentration of hydrogen ion, by the way, because you just solved for the pH. Okay, well that pretty much wraps up calculating the pH of acids and bases. It's a lot of information. You need to practice it, and certainly come back and listen to parts of this PowerPoint, this podcast, and look at this PowerPoint if you need to. Okay, let's see. I was asked to make a funny, let's see. Neutron walks into a restaurant, asks for a Coke, asks how much it is. Waiter replies, "For you, no charge." Get it? It's a neutron. It has no charge. If you haven't heard that one yet, shame on you. You're not enough of a dork if you're still out of the loop on geeky chemistry jokes. Alrighty, I hope you have a great day. Have fun. Bye.